Hello class. So on this video, we're starting the session or sequence of videos which are not required for you to watch. It's just selected topics that I want to introduce to you, which because you'll probably see them further on in your careers. In fact, this particular topic you'll most likely see further in your careers, especially for a lot of the engineering majors. You're going to see systems of ODEs a lot. Okay? So we'll go over this material. I think I will need only today, so this lecture and then tomorrow's lecture to finish this. If I do, I'll do one more topic on a different topic. I'll do one more video on a different topic. If not, then I'll just do this topic. But I went through all the topics I was thinking of doing, and this is definitely the one that I thought was most important for you. So even if we just get through this topic, then I think it's still a lot of good information for you to have. That's a good introduction for when you see it in your more advanced classes. Now, I didn't follow this from the book, but I'm pretty sure it's very similar. I did notice that it is in chapter 7. So if you want to see how they define and do all this in the book, you can go through chapter 7. But again, you don't have to. Everything that is needed to be defined is going to be here in these videos. So first, what we're going to do is define what a system of first order, and that's one thing. We're going to only be working with first order ODEs, but still, there's a lot we can do with just this. All right, so let's see what a system of first order linear. That's another thing. So first order linear ODEs are the ones we're going to focus on. All right, so what's a system of first order linear ODEs look like? Okay. So first, suppose you have, in this case, n dependent variables, right? So n different dependent variables. Usually we've been working with only one dependent variable, usually y, right? Now we're going to have n dependent variables. We're going to call them x sub 1, x sub 2, up to x sub n. We want these to be ODEs, right? So we're going to have a single independent variable t, right? Which means that x1, x2, up to x sub n are all functions of t, right? So a system of first order linear ODEs has this general form. You have x1 prime equal to some function of t times x1 plus some function of t times x2 up to, all the way to some function of t times x of n plus some function of t, which we call g sub 1. Now, notice that if we focus on, so there's more, there's more equations in this system, but for now, let's say we just focus on this particular equation, just one equation. Notice that this is linear. Right? How do we know it's linear? Again, let's follow the same definition as before. Okay, so let's check that everything that is a derivative only in front of it, or the coefficient that's in front of these terms, is only a function of t. Okay? So we have x1 prime. Okay? There's a 1 in front of it. Okay, that's a function of t. It's an expression only involving t's and constants. Here we have the zero derivative of x1. You can check that whatever's in front of it, just by definition, is just an expression involving t and constants. Same for all of the other dependent variables. And again, remember that just the function x of n, or x of I, is the same as the zeroth derivative of the function. Right? So every term that has a derivative, the coefficient is a function of t, and then the term that doesn't have any derivatives, right? Which means no derivatives of the x of i's or the x of i's themselves. What's in front of it is again a constant, right? And the function itself is just a function of. Oops, sorry. Let me not write that. Let me just say it like this, more simply. Whatever is not multiplied by any derivative is by definition a function of t, which is an expression only involving t's and derivatives, right? So no dependent variables show up where they're not supposed to. So this differential equation, just by itself, is linear. And you can verify that this is going to be the case for each of the ODEs we have here, just thought of separately, not as part of the system, but by themselves. Okay? So all of these are first order, right? Because we only have a first order derivative, and they're all linear. Now, what makes it a system is the fact that we don't have only one of them, right? In this case, we have n of them. So the order of the system is how many equations you have, and how many equations you have is determined by how many derivatives you have, right? In this case, we have n derivatives, like one derivative for each function, dependent variable or function x of I, right? So we have n linear first order ODEs, right? So all of them put together constitute a system, of first order ODEs. You can think of it as an nth order system because there are n equations in it. Now, this is going to be the most general form, and I gave you this most general form because so we're going to be focusing mostly on the 2 by 2 case. So when we have two dependent variables and two derivatives, right? So only two equations in our system, but everything we do for that case is going to generalize to the most general case, which is given by this, where you have n equations. So that's why I give it to you in the general case, although, again, for most purposes, we're only going to be working with two equations in two dependent variables. Now, when we use 3 or less dependent variables, which is usually the case in any class, if we have 3 or less dependent variables, we're usually just going to call them x, y, and z. Right? So that's why I wrote here. Think of x1 as just being x, x2 as being y, and x3 as being z. Right? So in the examples, when we work with only 2 dependent variables, those are going to have names x and y, and the independent variable is always going to be t. Okay? Now, what we're going to do is we're going to write this system here, 1, in terms of matrices. So first, we're going to define this matrix, or this vector. Right? So what is a vector? A vector is just a column matrix. So a matrix with only one column. Right? So whenever I say vector, just think of a matrix with only one column. Okay? So we're going to, anytime we have a vector, we're going to label it with this sort of arrow on the top to just to make it clear that it is a vector, right, compared to a matrix. Right? So matrix is going to have more than one column. A vector is going to have only one column. So matrices, I'm not going to write anything on top. For vectors, I'm going to write this sort of arrow shape on the top. Okay. Now, if we let x of t be equal to x1, x2, xn, right? It's just this matrix whose entries are the dependent variables. Right? At be the matrix whose entries are the functions of t in each equation, right? So these functions of t, right, in all of them. Right, so you have a11 of t, a12 of t, all the way to a1n of t. And then notice something here in the way I wrote this system. I wrote the subscripts in a specific way so that they're easier to interpret. So you notice that each a function here, so each a of t has two subscripts. Right? So for example, here we have oops, I didn't want to erase. Here we have the subscript 1, 1. Here we have the subscript 1, 2, up to 1n. Right? So the first subscript is always going to be what equation you're in. Right? So this is equation 1. Right? When we're ordering as, the equation involving the first derivative, x of 1 prime, being the first equation, the equation involving the derivative x2 prime being the second equation, etc. Right, so the first subscript is always going to tell you what equation is this function in. Right, so similar here, the first subscript is a 2 because we're in the second equation. Here, the first subscript is an n because we're in the nth equation. The second subscript tells you what dependent variable is this function multiplying. So for example, here, the first subscript is a 1, which means the second subscript, is a 1, which means we're multiplying the first dependent variable x of 1. Here, the second subscript is 2, meaning that this function is multiplying the second dependent variable x of 2. Here, the second subscript is an n, meaning that this function is multiplying the nth dependent variable. And then similar here, the second subscript here is 2 because this function is multiplying the second dependent variable, etc. So the way I wrote the subscripts is important just for us to organize things better when we write things in matrix. So again, the first subscript tells you what equation you're in terms of the matrix, what row you're in. Second subscript tells you what dependent variable your function is multiplying. And in terms of the matrix, it's telling you in which column you're in. So let me write a note of that here. Let me write it on top because I don't actually have enough space. So first subscript tells you what equation or row, if we're talking about the matrix, you are in. And the second subscript tells you what dependent variable you're multiplying, which is the same as saying what column in the matrix. So having said that, when we go here to the matrix, you can see that everything matches. Everything in the first row has first subscript 1, and everything in each column has the same subscript. Right? So everything with second subscript 1 is in the first column, everything with second subscript 2 is in the second column, up to everything with second subscript n is in the nth column. So this matrix A, in this case, is an n by n matrix. Actually, let me do that in a different color just to distinguish it. Let me use purple. Okay. This vector, again, is a matrix, it's only one column. It has n rows, so this is an n by 1. Okay. And then finally, there's one more vector we have to define. We're going to define this vector g of t, which is just the vector containing each of the functions g sub I at the end. Right, so in each equation, we have a function g sub I that's not being multiplied by by any dependent variable or their derivatives. Right? So that is what g of t is. The entries are these g sub i's. So again, this is a vector because it's a matrix with one column. There's n of them, n entries, so it's an n by 1 matrix. Right? Finally, let's define the vector x prime as the entry-wise derivative of x. Meaning that, what is x prime of t? This vector looks like x1 prime. Oops, let me make it a little bit longer. Right, this is x1 prime, x2 prime, up to xn prime. Right, so it's just taking the derivatives of the functions in x. Now, having defined these three matrices, and again, x and g, we call them as vectors, and you can see that in g, I also have this arrow symbol on the top. If we write things like this, then we can simply rewrite this system of n linear first order ODEs, right? Instead of writing it in this long form, we can just write it as x prime of t equals a times x plus g. In the case that we have a non-homogeneous system of equations, in this case we do, right, because we have things that are not being multiplied by the derivatives of the dependent variables. Right? In the case that all of the g sub i's are 0, we would have a homogeneous system, in which case we could rewrite it as here as just x prime equals a times x. So again, just as a summary of what we did. Right? If we have a nth order system of first order linear ODEs, means that we have n equations with n derivatives and n dependent variables. And in general, our system is going to look like this, as I wrote in 1, which we can simplify by defining these matrices as either equation 2 or equation 3, depending on whether our system is homogeneous or not.